Physical models are a vital tool for scientists to better understand the mechanics and dynamics of plate tectonics on the Earth's surface. This model was created to show the key processes and geological characteristics within certain plate boundaries. The plate boundaries represented within the model are divergent and convergent boundaries, specifically of oceanic-oceanic divergent boundaries and the subduction of oceanic continental boundaries in a convergent boundary. This model is representing the divergence of oceanic-oceanic crust. To greater understand the process, we begin at the underlying magma, often called the asthenosphere in context to the hot semi-fluid upper mantle. Magma is a hot viscous fluid, so it convects within the mantle. This convecting mantle is the driving force behind the movements of plate tectonics, and within the model, this darker red colouring is highlighted as it represents the hot magma rising from deep within the mantle. The lithosphere and oceanic crust is pushed up and away in opposite directions in order to make space for this rising new, hotter material, like the process of boiling water. This pressure on the lithosphere causes the lithosphere and crust to thin and then eventually break apart, as shown in how the hot magma extrudes through both the lithosphere and the oceanic crust within the model, causing seafloor spreading and lifting, forming the characteristic ocean ridges as shown in the model here. The grey outlining the mid-ocean ridge is representing an area of igneous formation as the forming of new crust. There are four main identifiable layers. The first is chambers that hold magma, and as they cool, they create a larger rock called gabbro. The second is the cracks in the oceanic crust that magma is fed through that create vertical walls of basalt called basalt dikes. Then there is fast-forming igneous rocks created by magma that erupts out of the seafloor, forming pillar basalts. And then finally, the ocean will deposit sediment onto the floor of the ridge. The bullseyes within this model are used as symbols for common earthquake focus areas. And the earthquakes at oceanic divergent boundaries are typically very shallow and mild, usually along the fault lines. The fault lines on the model are placed next to the diverging boundaries, as fault lines are usually most abundant near the boundaries due to the increased tension and pressure occurring along the boundaries. Another common geological feature is abyssal hills. The magnetic orientation actually changes as the iron particles within the rocks will orient to the Earth's magnetic field at the time of solidification. The model represents this polarity switch through arrows representing the switch of the north and south poles. A common example of divergent oceanic boundaries is the Mid-Atlantic Ridge. This ridge is a divergent boundary that spans the Atlantic Ocean, producing about 2.5 centimeters of new seafloor a year. Other examples include the East Pacific Rise and the Red Sea Rift. There are some limitations regarding this model. The foam model is a small scale of the true geological process of diverging boundaries and is focused on the generalized, typically universal aspects of divergent plate boundaries, so fine details and unique features are not included in the model. 2. It does not represent the true scale, as it is meant for easily identifiable visual comprehension of divergent boundaries, and so the scale accuracy is not accurate in comparison to the real-life tectonic plates. 3. It does not account for the ever-changing and dynamic nature of tectonic plates, as it is a static model of the divergent plate boundaries. 4. The foam material used limits showcasing aspect of divergent boundaries to static and physical properties, making it unable to replicate actual tectonic movements, convection current movement, and seafloor spreading. 5. The foam materials are not true replacements for rock and give no indication about the true mechanics of rock geology. Convergent boundaries. This is a modelling of an oceanic boundary subducting underneath a continental boundary, due to the oceanic boundary being denser and thinner compared to the continental boundary. The red colouring is representing the formation of magma as the subducting crust partially melts, as it is subjected to heat and pressure as it travels further down the mantle. This melted rock, known as magma, is less dense than its surroundings, so it rises through the continental crust, gradually interacting and assimilating with minerals within the crust and becoming more felsic and therefore volatile, until it erupts as a volcano, in this case a stratovolcano. This stratovolcano shown within the model are a common site of convergent boundaries, and these lines and layers are showing the layering of the viscous lava, ash, pyroclastic deposits that had hardened on the surface of the Earth's crust, forming the stratovolcano. The stratovolcano is a significant site of igneous activity, as a volcano creates igneous rocks through volcanic eruption, as lava quickly cools to become igneous rocks, as well as the cooling and crystallization of magma beneath the surface. Another geological feature of subduction zones is the trench. This trench is the result of the subducting oceanic plate, as the friction and pressure of the subducting plate being pushed into the mantle, creating the trench depression within the ocean floor. Oceanic trenches are also often associated with the subduction zone, due to the consideration that the trench is commonly where the subduction zone begins. Due to this intense compression and tension around the boundary, fault lines occur. Fault lines are weak areas of the crust that crack under the compressional and tension forces occurring at the plate boundary. The most common faults associated with subduction zones are megathrust faults, caused by the stress created by subducting plates pushing against the overriding plate. Megathrust faults are common in the areas of compression. These faults are capable of generating extremely large earthquakes, known as megathrust earthquakes, through releasing the stored energy. The bullseye is again used to symbolize the common focus of earthquake activity within subduction zones. Earthquakes can happen at any location of subduction plate for varying reasons. Shallow earthquakes are due to the tension build up from the subducting plates being forced beneath the overriding plates, creating friction and stress. Intermediate earthquakes to deep earthquakes occur because of the plate bending and cracking within the mantle, as well as reactions to the process like the dehydration of the plate as it sinks within the mantle. A common example of a converging oceanic continental plate is the Nazca Plate subducting underneath the South American plate, creating geological features such as the Andes mountain range, the Peru-Chile Trench, as well as megathrust earthquakes, such as the 2010 Maule earthquake. It has also created extensive volcanic activity as stratovolcanoes, like the one shown in the model, and volcanic arcs. Limitations. The scale and representation. The model is a simplified representation of the true processes of oceanic continental convergence zones, designed for clear visual concepts of the characteristics of the boundaries, so the scale of the tectonic crusts and other aspects in regards to real-life tectonic plates would be inaccurate.